Right. Hi, everyone. My name is Jeremy, and I'm a PhD student at the University of Michigan. For this video, I will present our latest research on designing the next generation of sound awareness systems. And in a world where sound orchestrates much of our daily lives, definitely hard of hearing individuals navigate a landscape where this sound information is not fully accessible, which fundamentally alters their interaction with the environment and the social structures. So to address this, prior researchers in HCI have proposed numerous sound awareness systems, ranging from early methods like sound visualization to more advanced AI-based systems that use deep learning models to recognize sound events. These AI-based systems like SoundWatch, for example, have demonstrated fairly good accuracy in terms of recognizing sound events in a lab setting. But a recent field study where we deployed the SoundWatch to deaf and hard of hearing individuals in the wild showed that these AI-based systems were prone to errors due to challenges in distinguishing acoustically similar sounds. For example, one participant reported that SoundWatch tended to recognize the sound made by the winter jacket sleeves as birds chirping. And another example of these errors took place in a more critical setting. So while one participant was in the hospital, the SoundWatch system incorrectly identified the hot monitor beeps as the smoke alarms, which caused some confusion and panic. So the problem comes, how can we make AI-powered sound awareness systems work better and more harmoniously with definite hard of hearing individuals' context of use? So most state-of-the-art sound awareness systems rely on the AI models to recognize and classify sounds, which struggle to address potential errors when encountering sounds with similar characteristics. And more importantly, these systems do not have the contextual knowledge as they mostly rely on a single stream of the audio input from sensing devices like microphones. But a good thing is that we humans do have the ability to perceive and acquire knowledge about the situated contexts. So this fact motivates us to develop a brand new approach to designing sound awareness systems, and we call it the human AI collaborative sound awareness. And so, as we mentioned, traditional systems sense sounds from the environment and output discrete sound sources or sound events. But the HACS-based systems, on the other hand, will output sound characteristics. And this kind of switch addresses the challenges of AI systems in terms of distinguishing acoustically similar sounds. And the system will then inform the deaf and hard of hearing users of the recognized sound characteristics. So since the users know various kinds of information, like the locations, the presence of objects or people, ongoing activities, and so on, this effectively addresses the lack of information from the AI system side. With both the sound characteristics, information, and the contextual knowledge, the users will be able to make an informed prediction of the sounds in their environments. So here's an example of how the HACS-based system works. So imagine a user is hiking and the system reports a sound characteristic is sun liquid flowing. So based on the contextual information like hiking nature, the users can reasonably identify the sound as a river stream. Now, same kind of sound characteristics, but in a bathroom context. Unless it was like a very fancy mention, chances are the sound being a river stream will be very low. So the users may instead recall that they forgot to turn off the tap, hence the water flowing into the sink. So in short, the idea of the HACS is that sounds with similar characteristics can mean different things across different contexts. The HACS prompts machines to identify sound characteristics and help deaf and hearing users infer the present sound using the contextual knowledge. Now, I have intentionally left one piece of the puzzle left unaddressed. So we have mentioned the sound characteristics as the HACS-based system's output, but what exactly is this sound characteristics, and how can we define them? Well, we argue that this should satisfy two important criteria. First, it needs to be machine recognizable and classifiable. Second, it needs to be intuitive for the deaf and hard individuals to understand and comprehend. And so far, none of the existing sound classification solutions does both well. So, therefore, we started constructing a new sound taxonomy. This process is a collaborative effort from the stakeholders, including ASL interpreters and the card writers. And the research team first selected 18 source ambiguous sounds from the audio set that covered all sound events that deaf and hard of hearing people deemed important to be aware of from prior work. This list includes, sounds like beep, crumbling, or sizzling, and we then conducted a formative study with 8 ASL interpreters and probed how sign language like ASL can be used to describe and categorize these kind of source ambiguous sounds. And at the same time, we also asked the card writers to kind of caption these sounds without mentioning their sources. For more information on this process, please see our paper. We arrived at a sound taxonomy that is friendly to deaf culture and inspired by the ASL, of course. It has 18 sound classes. And this taxonomy has 4 fields. The class labels are mostly generated by the card writers. And the ASL sound description outlines how the sound class can be described using the ASL. And we also provide some examples of sound events that may belong to these sound classes. So this new taxonomy describes the sound characteristics and bridges the gap between AI, the output from the AI, and deaf and hard users. And we conducted two preliminary evaluations to test the feasibility of the HACS approach. So for the first evaluation, we evaluate whether the information enclosed in the HACS taxonomy could help deaf and hard of hearing individuals identify sound events. So this study is set up as an online simulation of the HACS workflow. We played the sound clip and presented its sound class, and then the ASL interpreters described the sounds using the gloss described in the taxonomy. We then asked the participants to imagine being in this kind of provided context and identify the possible sound events. And this simulation surfaced two important insights that demonstrated the feasibility and, more importantly, the flexibility of the HACS approach. So first, participants were able to distinguish different sounds with similar characteristics across various contexts. So for example, one participant stated that a beep sound means a car honk while walking on a busy street. But if they're in a boba shop, it probably means that their pickup order is ready. And second, using the HACS simulation, the participants were able to recognize different sounds produced by the same source. So door slam and door knock, for example, belong to different classes due to the differences in kind of sounds these actions generate. And the second preliminary evaluation focuses on answering the question of, are the sound classes in the HACS taxonomy machine classifiable? And to answer the question, we train a sound recognition model based on this taxonomy. We first compiled sound clips from free sound and adopted the transfer learning based on a pre-trained CNN model and fine-tuned the model on our training set. So we evaluated the model using a clip level prediction and returned a near perfect accuracy, which further demonstrates the potential feasibility of training accurate models based on the HACS taxonomy. So we showed two things. First, our taxonomy is machine classifiable. Second, the HACS approach demonstrates its potential to help deaf and hard-of-hearing people accurately recognize sound events based on their varying contexts. So in conclusion, for this paper, we propose HACS, a brand new approach to designing sound awareness systems that prompts the human AI collaboration in achieving sound awareness. Specifically, the HACS allows deaf and hard-of-hearing users to identify sound events based on their knowledge of situated contexts and sound characteristics recognized by the AI models. And this approach also opens up a lot of opportunities for personalized sound awareness systems, where deaf and hard of hearing users can assign labels to the sound classes based on the varying contexts. And furthermore, designers can leverage the ASL sign descriptions from the HACS taxonomy and design sound feedback as sign language animations. These types of visualization could be more intuitive for deaf signers who use sign language to communicate, allowing them to use their contextual knowledge with the signs to recognize events accurately. So please see our paper for more details, and thank you for listening.